In this module, we will be studying solving linear system of equations. The concept of a system of linear equations is one of the most important mathematical concepts, as it has got a wide application in diverse fields like physics, chemistry, engineering, computer science, economics, etc. For mathematicians also, the theory of linear system is a topic of great interest, as it is a fundamental part of linear algebra, again a core subject of mathematics. The formulation of a system of linear equations corresponding to a given problem simplifies the work to a great extent, as the data for a given problem then becomes easy to handle and conveniently computable too. Once the system of equations is formulated, the next task is to solve the system by using some appropriate techniques so that some inference can be made regarding the system. Depending on the number of parameters or variables in the problem, the system will consist of a specific number of linear equations in a specific number of unknowns. Dealing with big scale real life problems, the system obtained may have a big number of equations which may be manually impossible to solve. To find the solutions for such systems, computational algorithms are available. In fact, the system of linear equations and its solution techniques are so widely accepted and applied that even systems of non-linear equations are often approximated by linear systems using some techniques of linearization, which is then appropriately and conveniently worked with. In this module, we will discuss some techniques for solving linear system of equations, which will all be on the basis of matrix algebra and associated concepts. In particular, we will discuss the methods like Cramer's rule, Gauss-Jordan, elimination, and solving the system using elementary row operations. Since the solution techniques discussed in this module make use of matrix algebra, we would briefly discuss some concepts of matrix theory as well, and then apply it later for solving system of equations. After studying this module, you shall be able to write the system of linear equation in matrix form, solve the non-homogeneous system of linear equation by using Cramer's rule, Gauss-Jordan elimination method, etc. Solve the homogeneous linear equation by using elementary row operation. Write the quadratic form of a symmetric matrix and classify the quadratic form. Let us commence our module with the understanding of some of the definitions and concepts. Determinant of a square matrix. Determinant of a square matrix A is a real number that can be associated with it through a particular pattern of calculations. It is denoted by determinant A. Determinant of a 2 into 2 matrix. Determinant of a 2 into 2 matrix A is the difference of the product of main diagonal elements and the product of secondary diagonal elements. Let A be equal to A, B, C, D, then determinant of A equal to A, B, C, D is equal to A, D minus B, C. Determinant of a 3 into 3 matrix. Let A be equal to A, B, C, D, E, F, G, H, I. Then determinant of A is equal to small a, E, F, H, I minus B determinant D, F, G, I plus C determinant D, E, G, H, which is equal to plus A times determinant of the 2 into 2 submatrix of A obtained by deleting the row and column headed by A minus B times determinant of the 2 into 2 submatrix of A obtained by deleting the row and column headed by B plus C times determinant of the 2 into 2 submatrix obtained by deleting the row and column headed by C. Similarly, determinants of matrices of higher order can be evaluated. Minors of a matrix. The minor Mij in the ith row and jth column of matrix A is given by the value of the determinant of the submatrix obtained from A by deleting ith row and jth column of matrix A. For example, each determinant of a 2 into 2 submatrix appearing in the above definition is called a minor of the matrix. For example, M11 is equal to EFHI, M12 is equal to DFGI, M13 is equal to DEGH. Cofactors of a matrix. The cofactor Cij corresponding to the ith row and jth column of matrix A is the minor associated with a sign which is specified by the following formula. Cij is equal to minus 1 raised to the power of I plus j Mij, where Mij is the minor in the ith row and jth column of matrix A. Cofactor matrix. The cofactor matrix C is the matrix formed by positioning the cofactor Cij at the ijth position of the matrix, that is C11, C12, C13, C21, C22, C23, C31, C32, C33. Adjoint of a matrix. Adjoint of a matrix A is the transpose of the cofactor matrix. It is denoted by adjoint A. That is, adjoint A is equal to C11, C21, C31, C12, C22, C32, C13, C23, C33. Inverse of matrix A. Let A be a square matrix. The inverse of A, if it exists, is calculated by using the formula A raised to the power of minus 1, which is equal to 1 divided by determinant A into adjoint A, comma, where determinant A is not equal to 0. Elementary row operations. The following three operations are collectively called elementary row operations. However, the same operations may be applied to columns as well. Interchanging of rows, multiplying a row with a non-zero scalar, adding a multiple of one row to another row. The matrix obtained by using a sequence of elementary row operations is said to be a matrix equivalent to a given matrix. Matrix representation of a system of linear equations. Consider a n into n linear system of n equations in n unknowns given by a11x1 plus a12x2, which goes up to a1nxn, which is equal to b1, a21x1 plus a22x2, which goes to a2nxn, which is equal to b2. Then we go down to an1x1 plus an2x2, which goes up to annxn is equal to bn. Every linear system can be expressed in the following matrix form as A11, A12 to A1n, A21, A22 to A2n, and so on till AN1, AN2 to ANn. This has to be multiplied by x1, x2 right down to xn, which is equal to b1, b2 right down to bn, or ax is equal to b, where a is equal to aij n into n, x is equal to x I n into 1, and b is equal to bi n into 1. Augmented matrix. With reference to the stated system of linear equations, the augmented matrix is obtained from matrix A by adding to it the column representing the right hand side of the system. A11, A12 to A1n B1, A21, A22 to A2n B2, AN1, AN2 to ANn Bn. Row echelon form of a matrix. A matrix A is said to be in row echelon form if rows consisting of all zeros are at the bottom of the matrix. The first non-zero entry from the left is 1 in each row. This is called the leading entry. The leading entry 1 in each row is to the right of all leading entries 1 in rows above it. Rank of a matrix. The rank of a matrix is the maximum number of independent rows or the maximum number of independent columns. A square matrix of the form A n into n is non-singular only if its rank is equal to n. A set of vectors is said to be linearly dependent if one of the vectors in the set can be defined as a linear combination of the other vectors. If no vector in the set can be written in this way, then the vectors are said to be linearly independent. Next, we will study Cramer's rule. Let us consider a 3 into 3 linear system. A11x1 plus A12x2 plus A13x3 is equal to B1. A21x1 plus A22x2 plus A23x3 is equal to B2. A31x1 plus A32x2 plus A33x3 is equal to B3. The matrix form of this system can be written as AX is equal to B, where A is equal to A11, A12, A13, A21, A22, A23, A31, A32, A33, comma, X is X1, X2 to X3, B is equal to B1, B2, B3. To make use of Cramer's rule to solve the system of linear equation, we introduce three associated matrices which are formed by replacing one of the columns of matrix A by column vector of matrix B on the right hand side of the system of equations. We consider the following matrices. AX1 is equal to B1 A12 A13, B2 A22 A23, B3 A32 A33. AX2 is equal to A11 B1 A13, A21 B2 A23, A31 B3 A33. AX3 is equal to A11 A12 B1, A21 A22 B2, A31 A32 B3. By Cramer's rule, the values of the unknown variables is given by x1 determinant of ax1 divided by determinant A, x2 is equal to determinant ax2 divided by determinant A, x3 is equal to determinant ax3 divided by determinant A. As it can be seen by the expression for x1, x2, x3, if determinant A is equal to 0, then Cramer's rule cannot be applied. Solve the following system of equations. 2x1 plus x2 plus x3 is equal to 3, x1 minus x2 minus x3 is equal to 0, x1 plus 2x2 plus x3 is equal to 0. Solution. The system can be written as ax equal to b, where a is equal to 2, 1, 1, 1 minus 1 minus 1, 1, 2, 1, x is equal to x1, x2, x3, and b is equal to 3, 0, 0. Now determinant A, which is equal to 2, 1, 1, 1 minus 1 minus 1, 1, 2, 1 is equal to 3. Determinant AX1 is equal to 3, 1, 1, 0 minus 1 minus 1, 0, 2, 1, which is equal to 3. Determinant AX2 is equal to 2, 3, 1, 1, 0 minus 1, 1, 0, 1, which is equal to minus 6. And determinant AX3 is equal to 2, 1, 3, 1, 1, 0, 1, 2, 0, which is equal to 9. Using the formula given by Cramer's rule, x1 is equal to determinant ax1 divided by determinant A, which is equal to 3 divided by 3, which is equal to 1. X2 is equal to determinant ax2 divided by determinant A, which is equal to minus 6 divided by 3, which is equal to minus 2. X3 is equal to determinant ax3 divided by determinant A, which is equal to 9 divided by 3, which is equal to 3. Hence, the system has a unique solution given by x1 equal to 1, x2 equal to minus 2, and x3 equal to 3. Solve the following system. x1 minus 2x2 minus x3 is equal to 3. 2x1 plus 3x2 plus x3 is equal to 1. x1 plus 3x2 minus 4x3 is equal to 8. Solution. Here the coefficient matrix A is given by A is equal to 1 minus 2 minus 1, 2, 3, 1, 1, 3 minus 4. Here it can be seen that determinant A is equal to 0. Hence the system does not possess a unique solution. By using other techniques which are discussed later, it can be seen that this system has infinitely many solutions given by minus 5x3 minus 7, 3x3 plus 5, x3, where x3 is an arbitrary real number. Let us discuss solutions by elementary row operations. As seen in the definitions earlier, there are three elementary row operations. We will now make use of these elementary operations to solve a system of linear equations. The basic idea behind this technique is that by making use of elementary row operations, the inverse of coefficient matrix A is found, provided it exists. Consider the matrix form of the system of equations given by Ax is equal to b. This is equivalent to a raised to the power of minus 1, Ax is equal to a raised to the power of minus 1b, provided a minus 1 exists, or a minus 1a into x is equal to a raised to the power of minus 1b, or 1x is equal to a raised to the power of minus 1b, or x is equal to a raised to the power of minus 1b. So, solutions to the system is given by a raised to the power of minus 1b. Now, to determine a raised to the power of minus 1, we will make use of the following facts. If E1 is the elementary matrix that is obtained when a particular elementary row operation is performed on the identity matrix I, then the product of matrix E1 and A is same as the matrix resulting from A if same elementary operation is applied on A. In other words, performing an elementary row operation on A is equivalent to multiplying A on the left by the corresponding elementary matrix. Now, if A is invertible, then a sequence of elementary row operations will transform A into an identity matrix. And as applying an elementary row operation on A, it is equivalent to multiplying A on the left by the particular elementary matrix, so that we have Ek into Ek minus 1, which goes on to E2 E1A, which is equal to I. This is the same as Ek minus 1, which continues to E2 E1, which is equal to a raised to the power of minus 1. So, the technique simply reduces down to the computation that initiates by considering the augmented matrix A divided by I and applying same elementary row operations on I as on A, so as to transform A into I. The matrix obtained from I is the desired matrix A raised to the power of minus 1. Now, this matrix A raised to the power of minus 1 is used to find the solution given by A raised to the power of minus 1b.
Solve the following system of linear equations. 2x2 minus x3 is equal to minus 2. 5x1 plus 2x2 plus 3x3 is equal to 4. 7x1 plus 3x2 plus 4x3 is equal to minus 5. Solution. Here A is equal to 0, 2, minus 1, 5, 2, 3, 7, 3, 4. Clearly, determinant A is not equal to 0. So, solution is given by x is equal to a raised to the power of minus 1b, where b is the matrix on the right hand side. Consider the augmented matrix. A divided by I is equal to 0, 2, minus 1, 5, 2, 3, 7, 3, 4 divided by 1, 0, 0, 0, 1, 0, 0, 0, 1. Now, what we have, this is equal to 5, 2, 3, 0, 2, minus 1, 7, 3, 4 divided by 0, 1, 0, 1, 0, 0, 0, 0, 1. As R1 tends to R1 divided by 5 and R3 tends to R3 minus 7 R1, what we have is 1, 2 by 5, 3 by 5, 0, 2 minus 1, 0, 1 by 5 minus 1 by 5, divided by 0, 1 by 5, 0, 1, 0, 0, 0 minus 7 by 5, 1. R2 tends to 1 by 2, R1 tends to R1 minus 2 by 5, R2, R3 tends to R3 minus 1 by 5, R2. We have 1, 0, 4 by 5, 0, 1 minus 1 by 2, 0, 0 minus 1 by 10 over minus 1 by 5, 1 by 5, 0, 1 by 2, 0, 0, minus 1 by 10, minus 7 by 5, 1. As R3 tends to minus 10 by R3 and R2 tends to R2 plus half R3, R1 tends to R1 minus 4 by 5 R3, we have 1, 0, 0, 0, 1, 0, 0, 0, 1 divided by minus 1, minus 11, 8, 1, 7, minus 5, 1, 14, 10. So, the inverse of a coefficient matrix is given by a raised to the power of minus 1, which is equal to minus 1, minus 11, 8, 1, 7, minus 5, 1, 14, minus 10. Hence, the solution of the given system is x is equal to a raised to the power of minus 1b, which is equal to minus 1 minus 11 8, 1 7 minus 5, 1 14 minus 10 into minus 2 4 minus 5, which is equal to minus 82 51 104. Hence, x1 is equal to minus 82, x2 is equal to 51, and x3 is equal to 104.
It can be checked that the above stated values of x1, x2 and x3 satisfy all three equations of the given system. Note, for a system of linear equations, if determinant A is equal to 0, then A minus 1 does not exist and the system is either inconsistent or has infinitely many solutions. If A minus 1 exists, then the system is consistent and has a unique solution. The method discussed above is the case of unique solution. In case the system possesses infinitely many solutions, identity matrix cannot be obtained from the coefficient matrix A using row operations.
Example 2. Solve the following system of linear equations. x1 plus 2x2 plus 4x3 is equal to 1, x1 plus 3x2 plus 9x3 is equal to 2, x1 plus x2 minus x3 is equal to 0. Solution. Here A is equal to 1, 2, 4, 1, 3, 9, 1, 1, minus 1. Clearly, determinant A is equal to 0. Hence, the system is consistent. Let us now consider the augmented matrix, which is equal to 1, 2, 4, 1, 3, 9, 1, 1, minus 1 divided by 1, 0, 0, 0, 1, 0, 0, 0, 1. R2 tends to R2 minus R1. R3 tends to R3 minus R1, which is 1, 2, 4, 0, 1, 5, 0, minus 1, minus 5 divided by 1, 0, 0, minus 1, 1, 0, minus 1, 0, 1. R1 tends to R1 minus 2 R2 and R3 tends to R3 plus R1. We have 1, 0, minus 6, 0, 1, 5, 0, 0, 0 divided by 3 minus 2, 0, minus 1, 1, 0, 0, 1, 1. At this point, it can be clearly seen that no further row operations can transform the coefficient matrix A into an identity matrix. Hence, this is the case of infinitely many solutions.
Moving on to solution by Gauss-Jordan elimination method. In Gauss-Jordan elimination method, again elementary row operations are used with a particular approach so that the coefficient matrix A would be transformed into its reduced row echelon form. The row echelon form, as discussed in definitions, would be obtained by using elementary row operations. If leading entry 1 in a row is the only non-zero entry in its column, then the matrix in the reduced echelon form readily provides us with the solution for a given system. Again, the augmented matrix is formed for the given system, reduced to the desired form, and the equations are again formulated corresponding to the reduced matrix. The matrix, which is in the simplified form, provides the solution by using back substitution.
Example. Solve the following system of linear equations. x1 plus x2 plus x3 equal to 5, 2x1 plus 3x2 plus 5x3 is equal to 8, 4x1 plus 5x3 is equal to 2. Solution. The augmented matrix is formed as 1, 1, 1, 2, 3, 5, 4, 0, 5 divided by 5, 8 and 2. We now perform row operations to get reduced echelon form. R2 tends to R2 minus 2R1, R3 tends to R3 minus 4R1. 1, 1, 1, 0, 1, 3, 0 minus 4, 1 divided by 5 minus 2 minus 18. R3 tends to R3 plus 4R2, 1, 1, 1, 0, 1, 3, 0, 0, 13 divided by 5 minus 2 minus 26. R3 tends to R3 divided by 13 and R2 tends to R2 minus 3R3, which is equal to 1, 1, 1, 0, 1, 0, 0, 0, 1 divided by 5, 4 minus 2. This is the required echelon form. We formulate the equations from the reduced augmented matrix obtained above. x1 plus x2 plus x3 is equal to 5, x2 is equal to 4, x3 is equal to minus 2. By back substitution, we get x1 is equal to 5 minus 4 plus 2, which is equal to 3. Hence, the solution is x1 is equal to 3, x2 is equal to 4, and x3 is equal to minus 2. Example 2. Solve the system. 4x2 plus x3 is equal to 2, 2x1 plus 6x2 minus 2x3 is equal to 3. 4x1 plus 8x2 minus 5x3 is equal to 4. Solution, augmented matrix. 0, 4, 1, 2, 6 minus 2, 4, 8 minus 5 divided by 2, 3, 4. In the similar manner, we apply a sequence of row operations and get the reduced echelon form as 1, 0, 7 by 4, 0, 1, 1 by 4, 0, 0, 0 divided by 0, half 0. The system of equations can now be written for the reduced augmented matrix. Equations are x1 minus 7 by 4 x3 equal to 0 and x2 plus 1 by 4 x3 equal to half. It can be seen that since last row of the matrix is the row of all zeros, so we cannot obtain any specific solution for x3. Hence, x3 can be chosen arbitrarily, say k, that is x3 is equal to k. Then minus as x1 is equal to 7 by 4 x3, so x1 is equal to 7 by 4 k. x2 plus 1 by 4 x3 is equal to half, so x2 is equal to half minus 1 by 4 k. Hence the solution is x1 is equal to 7 by 4 k, x2 is equal to half minus 1 by 4 k, x3 is equal to k is arbitrarily real number. Now giving different values to k, we get different values for the solution. Hence the solution is not unique. Instead, there are infinitely many solutions for the given system. Example 3. Solve the system. x1 plus 2x2 minus 3x3 is equal to 2. 6x1 plus 3x2 minus 9x3 is equal to 6. 7x1 plus 14x2 minus 21x3 is equal to 13. Solution, augmented matrix. 1, 2 minus 3, 6, 3 minus 9, 7, 14 minus 21 divided by 2, 6, 13. Using row operation, we get echelon form as 1, 2 minus 3, 0 minus 9, 9, 0, 0, 0 divided by 2 minus 6 minus 1. Now, if we formulate the equations from the reduced augmented matrix, we have x1 plus 2x2 minus 3x3 is equal to 2, minus 9x2 plus 9x3 is equal to minus 6.
It can be seen that the last row suggests that 0 is equal to minus 1, which can never be mathematically true. Hence, the given system has no solution or the system is inconsistent. Note, if the augmented matrix in the reduced echelon form has a row of all zeros, including right hand side of the column, this implies that the system has infinitely many solutions. The number of arbitrary parameters in the solution is same as the number of rows of all zeros in the reduced augmented matrix. If the augmented matrix in the reduced echelon form has a row of all zeros in the coefficient matrix, part equated to a non-zero entry in the column corresponding to the right hand side column of the system, then the system is inconsistent. So far we had been focusing on non-homogeneous system of equations, that is Ax is equal to b where b is not equal to 0 and the methods to solve them. We now discuss about the solutions of homogeneous system of equations.
Example 1, solve. 2x1 plus 4x2 plus 6x3 is equal to 0. 4x1 plus 5x2 plus 6x3 is equal to 0. 3x1 plus x2 minus 2x3 is equal to 0. Solution. Consider the augmented matrix. 2, 4, 6, 4, 5, 6, 3, 1 minus 2 divided by 0, 0, 0. Corresponding echelon form is 1, 2, 3, 0, 1, 2, 0, 0, 1 divided by 0, 0, 0. Corresponding system of equation is x1 plus 2x2 plus 3x3 is equal to 0, x2 plus 2x3 is equal to 0, x3 is equal to 0. By back substitution, it can be seen that the only solution to this delete system is x1 equal to x2 is equal to x3, which is equal to 0, which is a trivial solution. Example 2, solve. x1 plus 2x2 minus x3 equal to 0, 3x1 minus 3x2 plus 2x3 equal to 0, minus x1 minus 11x2 plus 6x3 equal to 0. Solution. The augmented matrix is 1, 2, minus 1, 3, minus 3, 2, minus 1, minus 11, 6 divided by 0, 0, 0. We have the following reduced echelon form: 1, 0, 1 by 9, 0, 1 minus 5 by 9, 0, 0, 0 divided by 0, 0, 0. The corresponding equations are x1 plus 1 by 9 x3 equal to 0, x2 minus 5 by 9 x3 equal to 0. In this case, x3 cannot be determined specifically, so x3 can be given arbitrary value, say k. Hence, the solution is x1 minus 1 by 9k, x2 is equal to 5 by 9k, and x3 is equal to k, where k is arbitrary.
Next, we will discuss homogeneous system of linear equations. Consider a homogeneous system of equations in which the right hand side of a system is a column of all zeros given by Ax equal to 0. Clearly, x is equal to 0 is always a solution for the homogeneous system, which is called the trivial solution to the system. A solution to the homogeneous system is said to be non-trivial if values of at least one of the variables is non-zero. Obviously, a homogeneous system can never be inconsistent.
Moving on to quadratic form, consider a n into n real symmetric matrix A. That is, A is equal to A raised to the power of t, and x be a n into 1 column vector. Then the quadratic form of matrix A is defined by q is equal to x raised to the power of t ax. Example A, 1, 3, 3, 1, which is a symmetric matrix. The quadratic form is given by q is equal to x raised to the power of t ax, which is equal to x1 x2 into 1 3 3 1 into x1 x2, which is equal to x1 plus 3x2 3x1 plus x2 into x1 x2, which is equal to x1 squared plus 3x1 x2 plus 3x1 x2 plus x2 squared, which is equal to x1 squared plus 6x1 x2 plus x2 squared. Finally, we will understand classification of quadratic form. A quadratic form Q is equal to x t a x of a symmetric matrix A is said to be positive definite if Q is greater than 0 for x not equal to 0, positive semi-definite if Q is greater than equal to 0 for all x and Q equal to 0 for some x not equal to 0, negative definite if 0 is greater than Q for all x not equal to 0. Negative semi-definite if q is less than or equal to 0 for all x and q is equal to 0 for some x not equal to 0. Indefinite if q is greater than 0 for some x and 0 is greater than q for some x dash x not equal to x dash. By the nature of quadratic form of a matrix, one can study various characteristics of a matrix. We state a few of them. If A is positive, definite, then rank A equal to n.
Remark, in case of non-homogeneous system, it has been stated that determination of the coefficient matrix has to be non-zero if the system is T. In case to have a unique solution, in case of a homogeneous system, consistence is always guaranteed, but uniqueness of solution is ensured if determinant of coefficient matrix is non-zero. However, if determinant is 0, then the homogeneous system has infinite solutions. This can also be checked in the above two examples.
If A is positive semi-definite, then rank n is greater than A. If A is negative definite and lambda I, where I is equal to 1 right up to n, are its eigenvalues, then lambda I is less than 0 for all I equal to 1 to n. If A is negative semi-definite, then lambda I, which is less than or equal to 0 for all I equal to 1 to n, and lambda I equal to 0 for at least one I.
Now let us summarize what we have learned. For solving a system of equations, three elementary row operations are used, which can be interchange of two rows, multiplication of a row with a non-zero scalar, addition of a multiple of one row to another row. A system of linear equations can be represented in its matrix form Ax equal to b, where A is the coefficient matrix, x is the column vector of unknowns, and b is the column vector of right hand side values of each equation. For solving a non-homogeneous system of equation, Ax is equal to b, where b is not equal to 0, one can make use of Cramer's rule, Gauss-Jordan elimination method, elementary row operations to find a raised to the power of minus 1, and then compute x is equal to a raised to the power of minus 1 b, provided a raised to the power of minus 1 exists. that is if determinant A is not equal to 0. For solving a homogeneous system of equation, Ax is equal to 0, trivial solution x is equal to 0 is the only solution if determinant A is not equal to 0, and a non-trivial solution exists if determinant A is equal to 0. A homogeneous system is always a consistent system. I repeat, for a symmetric matrix A, Q is equal to x raised to the power of t into Ax is its quadratic form depending on the sign of Q with respect to column vector x union Rn. The matrix A can be positive definite, positive semi-definite, negative definite, negative semi-definite or indefinite.